Hi everyone.
Hello, hi
Welcome.
everyone. Hi,
Welcome to
hi
Google
Jesse.
Developer Space channel. And thanks for tuning in to our live stream today. So today we are super excited to be hosting Data Science Singapore once again for their second meetup of the month. Do leave a comment in the live chats and let us know where you're tuning in from. Before we begin, let me briefly introduce who we are and what we do. Google Developer Space is a platform for developers and startups around the region to learn, connect, engage, and be inspired. As part of the developer relations team, we aim to empower and connect the community to our people, programs, network, and technologies, be it in person or online like today. Without further ado, I'll hand the stage over to Ivan from Data Science Singapore to start today's session. Over to you, Ivan.
Hi everyone. My name's Ivan, and I'll be the host and moderator for today. So thanks for tuning in this evening. Today's topic will actually be getting started on network science and analytics. We are pleased to have two speakers with us today. Prasanta is actually a research scientist from the Institute of High Performance Computing, IHPC, and adjunct assistant professor with the NUS Business School. He focuses on predictive and causal inference problems in large-scale social networks, and his research spans across different fields such as digital marketing, fintech, edtech context, and particularly in Asian emerging markets. Next, we have Daniel, who's a software engineer at Links Analytics for the past 6 years. And before that, he was a site reliability engineer at Google. So for those of you who are not familiar, LinksKite is actually an open source one-stop shop graph data science platform that will help improve machine learning performance in various applications. So without further ado, I'm going to hand over the time to Prasanta, who will begin the first part of the talk I shared by getting started with network analytics. So if you have any questions along the way, please leave them in the comment section below and we'll answer them during the intermission. So Prasanta, please.
All right, thank you, Ivan, and welcome all of you to this session on network science and analytics. So first of all, thank you very much on behalf of both Daniel and myself. We are really glad to have you with us on this session for the next 1 hour. So I have fairly modest expectations for this session because network science is, again, it's a very broad field, and I wouldn't even try to condense this information in just a 30-minute session. So what I'll try to do instead is give you a very quick introduction to this field, try to get you interested in some of the foundational concepts and emerging use cases that people have been working on with network science. And then hopefully you'll have enough information to appreciate the utility of network science when we look at a walkthrough with an actual real-world data set with LinksKite towards the later part of the session. So as Ivan mentioned, if you have any questions or comments along the way, feel free to drop it in the comment box, and we'll try to circle back to them at the end of my session. Right, so let's begin. So one of the questions that I keep getting quite often when giving talks or workshops on social networks is, why am I so interested in network science or broadly in the area of social networks? And honestly, I could give you one of thousands of possible reasons. But let me just start with a very fun example of why social networks look, it's really appealing to me. So if you're a Game of Thrones fan, this shouldn't come across as any surprise to you, but so there are a lot of interesting character dynamics in this particular TV show, right? So you have very complex relationships and power plays between the characters. What you see on the screen is actually a network of betrayals between the different characters of the show, as evidenced from the first 5 seasons of Game of Thrones. Okay, so what you'd immediately notice is that there are some nodes that are much larger in size, while there are others that are smaller in size. So in this context, the size of the node in this network is proportional to the number of betrayals that the node has either committed or have experienced in the course of the 5 seasons. Okay, so someone like Cersei Lannister, for example, is a huge node, right? Because if you've been following the show, you'd know that Cersei Lannister is always scheming and plotting, different kinds of episodes, and so you'd see Cersei Lannister playing a very central figure in this kind of a network. Now, you'd also notice that there are some links that are bold while others are dashed. And so what that implies in this particular visualization is that there are some acts of betrayal that are proven, but there are some acts that are more implied. Okay, so the dashed links are actually implied betrayals. Now, why am I showing you this? So even if you're someone who's been living under a cave and have no idea about this particular show, this is actually a very good example of how you could use a network representation of something as abstract as a television show to convey a lot of information about what the show is about, what are some of the the power dynamics in play, who are some of the central characters, etc. Right? So just by looking at this network, you're able to get a fair sense of what's happening in this TV show. Here's another fun example, and this one comes from the domain of food networks. So this was actually a study that was published back in 2011, and the study was on something else, looking at flavor compound sharing among ingredients. But this particular network that you see on the screen actually plots co-occurrence of ingredients in popular recipes worldwide. Okay, and I think this is based on an analysis of over 50,000 different recipes spanning countries and cultures. Now, again, a node here is an ingredient, and if two nodes co-occur in a particular recipe, you have a link between them, and the thicker the link, the higher the frequency of their co-occurrence. Okay, so what you would immediately notice when you're looking at this visualization is that there are some ingredients that are almost exclusive or specific to certain cultures or communities, right? Sesame oil, for example, doesn't find pride of place in the North American cuisine, for instance. However, there are certain ingredients like tomato and garlic that seem to be a crossover ingredients that kind of bridge different communities and cultures. Now, once again, you don't have to be an expert in food networks or culinary science to be able to look at this visualization and make some key inferences about people's eating habits around the world and how recipes over the years have evolved into what they are today, right? So again, this is a very interesting example of where you can use the idea of networks or graphs to tell a very compelling story just by using a single visualization. But that's not to suggest that the visualization aspect of networks are the most compelling use of social networks. We all live in a network society, right? So a good example of how networks affect all of us is just thinking about an MRT network that probably all of us have used at least some point of time or the other. So just like MRTs, most urban infrastructures tend to be network systems, right? So an MRT, for instance, is a set of stations that are connected by the tracks. Now, even if you don't think about MRTs as network systems, you actually experience the effect of a network system day in and day out. So this was actually an infographic that I picked up from Channel News Asia a couple years back. And this looks at the average delays that across different lines to really tell a story about which line is more delay prone as opposed to others, right? So obviously you'd notice that the newer lines, like the downtown line, has a lower propensity of facing a substantial delay as opposed to, say, the east-west line, okay? But why is this important from a network context? Now, as I mentioned, train networks are a very good example of urban systems that are networked. So what happens is when you have a delay or a fault in one particular line, it leads to a spillover of traffic to other linked or connected lines, right? So if you have a fault in the east-west line, people will stop taking that line and try to move over to another line that's linked to the east-west line. As a result, you would end up with things like these on platforms, which is basically a lot of congestion. Right? So even though we don't realize, we are actually experiencing network effects every day, even though we are not always cognizant that it's a network effect. So here's another good example, and I think this is perhaps more timely because we are living through a major health crisis at this point. But networks actually serve as very important public health sensors. And so what do I mean by public health sensors? Just by looking at what's happening in social networks, you can get early signals about what is happening in the broader population. So this particular network that you see on screen is actually from a study that was done roughly 10 years back, which with the H1N1, which was kind of a limited pandemic at the time. This was in 2009, which saw a particularly bad outbreak of both the flu as well as the H1N1 influenza in the US. And this study analyzed a sample of close to 700 students at Harvard and trying to figure out whether you can predict the spread of this disease as a function of the student network. So the sample of students were split into two groups. The first group was a randomly selected set of students from the undergraduate population at Harvard, which is around 6,600 at the time. And then the second group was a group of students that was selected based on the nominations made by the first group. So the first group of students that were randomly picked were asked to nominate a friend. And that served as the second group that was studied for this particular analysis. And what the authors found in the study was that the students that belonged to the second group, which was the friends group, actually showed a much quicker incidence of the epidemic as compared to the first group, which was basically a randomly selected set of students. Now, what's very interesting is they found in the study that the peak incidence of epidemics, so they were tracking the infections every day, and they found that for the networked group of students, the peak incidence of the epidemic happened nearly 14 days ahead of the rest of the students. And so they used that to argue that by observing how these infections spread through networks on campus, you are able to get an early sensing mechanism or an early signal of what's likely to happen to the broader population that's not networked to the focal students in due course, right? So this is actually a very good example of how social networks can serve a very important public health service. Right, so having said that, I think what might be very interesting to think about is a lot of these networks have utility in not just the use cases that I just covered, but also in your own respective areas of work. So what I'll try to do is, for the next couple of slides, give you just the nuts and bolts of how to think about constructing a sample network and how do you think about quantifying a network, which would then give you the right set of tools to conceptualize more complex models or understand how these network analysis tools work. So very simply put, a social network is a collection of nodes and edges, okay? So if it's a human social network, the individual nodes are essentially actors or individuals. The relationships or the links between nodes represent any kinds of, one can have any different kinds of meaning. So the relationships could be friendships, kinship ties, co-authors on a particular patent or a paper. It could be romantic relationships, co-workers, etc. So there are two key advantages of representing data in the form of a network. The first one, of course, is it lets you predict important things about the actors in your network. So for example, in the network that you see on the screen, we notice that there is a tie between Alice and Bob, right? So let's assume that Alice and Bob are friends. So you can use this network structure to then pose a predictive question about whom Alice is going to befriend next. Is it going to be Charlie? Is it going to be someone else in the network? So that's a predictive problem that you can solve by using this network structure. But there could also be a question about explanation and not just about prediction. So for instance, if I tell you that the next person to befriend Alice is Charlie, can you then come up with a plausible mechanism for why that might be the case? So why is it Charlie and not someone else? So there are many different kinds of problems that you can solve by representing a social behavior in the form of a network. So networks also serve important economic purposes. So if you're, for example, a digital marketer, the study of social networks might be very pertinent for you too. And here's a good example. So for example, let's go back to the couple that we've selected for this particular session today, Alice and Bob. So if Alice buys the latest iPhone, what is the likelihood or propensity that Bob will buy it too, right? So if Alice buys an iPhone and Bob is one of her friends, is it likely that Bob is going to buy an iPhone as well? Now, let's go a step further. If Bob decides to buy an iPhone, can we attribute that purchase decision to their friendship tie, right? So this is a question about causal inference. Can we attribute that decision to the fact that there is a structural link between the two of them, okay? And if we find evidence that there is this behavior of peer influence, then as a digital marketer, can you use that evidence to leverage, or can you leverage that evidence to create, say, marketing campaigns to increase the sales of the latest iPhone, right? So there are a lot of work in marketing, for instance, that leverages the idea of product contagion, product diffusion, and understanding like what are optimal seeding strategies in a network to promote a particular product or promote a particular service, all right? So this is a good example of where social networks can be useful. So going back to the example of a basic network, so networks can be broadly of two types. So you can have directed networks or undirected networks. So again, as the name suggests, a directed network is one where the links between two nodes have a direction. So a good example could be some kind of a flow or mobility. So we will see a good example of a directed network later on when Daniel presents the walkthrough of a mobility network data set. An undirected network could be something as simple as, say, co-authorship on a particular paper or a patent, right? So there's no essential sense of direction in that kind of a social tie. Now, the links could also could be either binary or could be valued. So binary link is basically 0 or 1. So you're either a friend or you're not a friend. A valued link or a weighted link has some kind of a weight attached to the tie, or some kind of a strength attached to that tie. So again, think of a mobility network. So the number of or the amount of traffic that flows through the link could be a proxy of the tie strength or the weight of the tie. So once you have that basic idea of how to represent a network in the form of nodes and edges and weighted and binary edges, the next question is, what about data structures? What are some of the more popular ways of representing network data when you're writing code, for instance? One of the earliest ways of storing network data would be adjacency matrices. So if you've done a course on discrete math, you'd be very familiar with the concept of an adjacency matrix. So it's basically a square matrix where you have a value of 1 if there is a tie between the two nodes, or a value of 0 or missing if there are no ties. Okay, so if you can see on the network on the screen that there is a link between A and B, so you see that the matrix value for A comma B is 1. Okay. Now, there are some obvious limitations with storing networks as matrices. So as you can imagine, if it's a really sparse network, you end up wasting a lot of space. It's not a very space-efficient way of storing network data. So there are obviously other better alternatives for doing that. So two common ways of storing network data that have emerged in more recent times is the adjacency list and edge lists. Okay. So these are space-efficient ways because you don't store null edges, right? So you're only storing information on edges that exist. So once again, we will actually be seeing a good example of an edge list later on in the session when we're looking at the mobility network data set. Right. So now that you have a very basic kind of an understanding of what a network looks like and what are some of the common data structures that are used, let's get into a concept that's perhaps the most popular idea that comes along when we talk about networks, which is the idea of centrality, right? So you might have heard about the concept of central nodes in a network. Now, central nodes are basically important nodes in some sense of the term, right? And so there are various ways by which you can classify a node as more important or less important. So it could be based on individual characteristics of the nodes. So if it's in a social network, you could be thinking of, the gender or the age of the particular person as some proxy of importance. But in the context of the network structure, you can think of some nodes as being more important or better embedded in the social network as compared to other nodes. So again, there are many measures of network centrality, and obviously I'm not going to cover all of them. I've mentioned a link to a very interesting R package on the slide called Sina. And so this is actually a fantastic package because it lets you analyze over 50 different types of centrality measures just by calling the respective functions. If you're interested in learning more about network centrality, you should definitely visit that particular R package. But just to give you a quick kind of overview of three popular measures of centrality. So degree centrality basically tells you the number of links that are either that are directed to the particular node or away from that particular node. Okay, so in the context of an adjacency matrix, the out degree of a particular node is basically the sum of, it's a row sum. Okay, so in the context of this network, if you can see the node C is connected to B, D, and E, so the out degree of C, so basically the links from C to other nodes sum up to 3. So that's the out degree of C. Whereas the in degree of C would be the number of nodes that link into C. Okay. Now, again, think about what these measures might mean in the context of a social network, right? So out degree would be the number of links from the node to others. So this could be a measure of some kind of network activity, right? How active is this node in the network? In degree, on the other hand, is a measure of how many of these links flow into the node. So maybe this could be a measure of popularity, right? How many people are trying to connect to you? Okay. So these different measures serve different purposes. So there are two other measures that I want to quickly highlight here. The first measure is called closeness, which is basically a measure of how close or far a node is from every other node in the network. So in terms of the measure, it's the inverse of the farness of a particular node. Farness of a particular node is basically the distance of that node to every other node in the network. So distance is the number of hops it takes to move from a particular node to another node. Okay, so closeness gives you a sense of how quickly you can move from one particular node to any other node in the network. So this is, again, you can think of contexts where closeness can be a very useful measure to model. And lastly, my favorite centrality measure is the idea of betweenness. And betweenness is basically, it gives you a sense of how many shortest paths in the network include you or pass through you. So it's a ratio of the number of shortest paths that include the focal node to all possible shortest paths in the network. Okay, so one of the common questions that you would think of when you study centrality measures is, well, given a network, can I figure out which is the most central node? And the answer to that particular question almost always is, well, it depends. It depends on what you are trying to model. So if it's a social network, maybe you're trying to model degrees of separation between individuals. If it's a supply chain network, maybe you're trying to model how quickly you can move a particular a supply from a particular warehouse to a second warehouse, right? So depending on what you're trying to model, certain nodes can be more or less central, right? So just to give you an example, in this particular network, you see there are different nodes that are considered central depending on what measure you're trying to model. Okay, so the node H, for instance, has the highest betweenness centrality. Now, I was thinking of what's a good example to give, or good analogy of where a high betweenness centrality makes a lot of sense. And I was reminded of this very recent Netflix show called Indian Matchmaking. And I don't know if any of you have actually found yourself on that particular page. And so if you've seen a couple of episodes of this show, you'd know that it's about this woman from Mumbai who's a marriage consultant, and she hooks up prospective marriage candidates across the US and India to suitable ties. And in terms of her network, and she is a perfect example of someone who has a high betweenness centrality, because she connects disparate parts of the network who don't have information about each other. And so she controls that flow of information between these different clusters, right? And so in the context of this particular show, her high betweenness actually gives her a very high brokerage potential, right? So if you want to find, at least in the context of the show, the perfect match for you, so as to say, you have to go through her, right? And that's what keeps her in a profitable business, okay? This is actually a good example of how high betweenness can come in really handy. Right. So now that we've covered the discussion on network centrality, for the final couple of slides, I want to quickly introduce you to some more popular machine learning concepts of prediction and causality, and how do you go about framing a predictive or causal problem in the context of a social network? So there are broadly two classes of predictive problems in graphs or social networks. The first class of predictive problem focuses on the idea of link prediction. So basically, given a set of nodes and links, can you predict the missing links, or can you predict future links? So that's a problem of link prediction. So what's a good example of link prediction? I think some of you might have already guessed this, but recommendation systems actually are a direct application of the link prediction problem in networks. So if you have a social network on, say, LinkedIn, or you're on Tinder, and you get recommended matches or connections, so on what basis are these recommendations made? So of course, they're made based on some similarities in attributes, individual level attributes like your age, or gender, or your interests. But it's also based on your network position, right? So if you know A and A knows B, but you don't know B, maybe B is going to be recommended to you just because it closes that triangle in the network, right? So your network structure plays an important role in what gets recommended to you. So the second class of predictive problems in social networks is about classifying labels at a node level. So if you're trying to classify nodes attributes into, say, label A or label B, or trying to predict a particular node level behavior, that's another example of a predictive problem, right? So maybe you have a network where a subset of nodes have certain labels, but you're using those labels plus the structural information to predict the label of a focal node. So then that's an example of a node attribute classification problem, right? So broadly, so any predictive problem that you see in social networks can be reduced to some variant of these two classes of problems. So a good example of, say, a node attribute prediction would be an example of an insurance fraud. So in insurance industry, a very common use case is looking at these claims of insurance event of accidents, and trying to figure out if the claim is likely to be fraudulent or not. So sometimes you have these giant fraudulent cartels or rings, where you have maybe the same individuals posing as the driver, the passenger, and the witness on different applications. And then you see a flood of different claim applications basically stemming from the same fraudulent individuals. So if you try to represent this kind of insurance fraud activity in the form of a graph, the whole situation becomes a lot more tractable, right? So you can now use this network and try to model this as a node classification problem, where you're trying to classify person 1 and person 2 and person 3 as fraudulent or not fraudulent, okay? So sometimes the structural information can come in very handy in making these classifications. Right. So the final part of this session really is about understanding what causal inference on networks looks like. And again, this in itself is a huge and very interesting area of work. It's something that I'm personally very interested in, but it's also a very complex area of research. So let me just frame this problem for you, so it helps you think about what this problem might mean for your own context of work. Okay. So again, let's go back to our example of Alice and Bob. So for Alice, if you design an intervention that affects Alice, it's likely to change her own behavior, right? So that's a standard causal attribution or causal inference problem. So if you see a change in behavior from Alice, you attribute it to some intervention that Alice has experienced. Now, if you think of Alice as one actor in a network, it becomes a network inference problem. So what happens when you introduce an intervention targeted at Alice, but it affects the local network of Alice, so friends of Alice, for instance, right? So a good example of this could be, again, the instance of Alice buying an iPhone. So the purchase of the iPhone can be a treatment, but then what does that do to friends of Alice in the network? Will they also be likely to get influenced by this behavior? And such kind of peer influence processes have been observed in almost every kind of behavior that you can imagine, from adoption of brands or products to diffusion of innovative services to the spreading of diseases and disorders to contagion in voting behavior, etc. So any and every kind of behavior is susceptible to this kind of influence at varying intensities or varying levels. But the problem in estimating causal inference in a network or a graph is that it's theoretically non-trivial to do. And here are 3 examples of why something like a randomized experiment or an A/B test is not as easy as it is in a non-networked setting. So one example or one challenge that you face is that when you're sampling individuals for randomization, as what you do in an A/B test, it's difficult sometimes to assign users in a treatment group while not assigning their neighbors to the same group. So when you're doing randomization, you have no control over whom you're assigning to which group, right? But think about of a user that you're assigning to a group where the treatment is a chat application, a video chat application. Now, if none of the user's friends are part of the treatment group, then who is this person going to chat with, right? So the experiment design gets a lot more complicated. So second challenge is that there's always the question of spillovers or network interference. So again, think of a connected graph, right, or a connected network. So if you assign a set of users to a particular treatment, how do you then guarantee that that treatment doesn't spill over to others who are somehow linked to these users, but but not in the treatment group, right? Because theoretically, they're all part of the same connected graph. So a clean separation of treatment and control is almost never possible. So you have to correct that using some kind of statistical means. And finally, preserving network, and this is linked to the first challenge, but preserving the network structure between treatment and control group is important because otherwise it's very hard to attribute the difference in the treatment group to just the treatment. Because someone can always argue that, oh, but the network structures in the treatment group are different from the control group, so maybe that plays a confounding effect, right? So my point of discussing all of this is A/B testing on network systems is a very active area of work in major tech companies. And there's a lot of research happening in this area. So if this is something that you're interested in, we should definitely talk offline. All right. So before I hand over to Daniel, I just want to leave you with some ongoing projects from the domains of finance and education that I'm personally very interested in working on. And hopefully these are things that would also pique your interest. So the first example that I want to talk about comes from the area of microfinance. So a lot of you who are working in the finance sector would be able to kind of relate to this context. So microlending or microfinance has emerged as a leading solution to the financial exclusion problem that plagues the bottom of the economic pyramid in many developing countries and emerging economies around the world, right? So there are many countries without formally established credit bureaus where it's very difficult to get access to credit. So you have a lot of these micro-lending companies that have come up that give small amounts of loans to borrowers at reasonable rates of interest without any collateral or financial history. But a critical challenge facing these microfinance institutions is that these institutions need very high repayment rates to sustain, because you need people to pay back their loans for these institutions to finance new loans, right? So we were working with a micro-lending company in an emerging economy in Asia. And the problem that I was specifically very interested in is to understand if there is some kind of a network effect in how people default on their loans. So what this means is if you have a group of borrowers and you have a certain subset of those borrowers defaulting on their loans, will that create some kind of a contagion effect on their connected peers? Would they start defaulting on their loans or not? Okay, so there's a question of peer influence in loan default behavior. The second question that I was interested in is, if we do find evidence of this kind of a network effect, would this differ based on some individual level characteristic like their credit risk of the borrower, right? So this is a quick kind of an overview of the sample of borrowers split into the low credit risk and high credit risk samples. So the red nodes on the screen are successful repayments. The blue nodes are are nodes who have defaulted, and the gray nodes are nodes about whom we don't have information. So we know that these exist, but we don't have information about them. So you can think of this as some kind of an egocentric network where you have information about a subset of nodes, but not others. So again, this is not surprising. You see that most nodes in the low credit risk sample tend to pay back their loans on time, while most nodes in the high credit risk sample tend to default. But what was interesting is once we fitted our network effects model on this particular sample, we were able to see two distinct distributions of network effects based on the level of credit risk that the borrower was exhibiting. So we found that in the low credit risk sample, most of the borrowers tend to exhibit very little network effects, which means they were almost not susceptible to whether their peers were defaulting or not. What was very interesting was that in the high credit risk sample, it was like a bimodal distribution of network effect. So there were a group of borrowers who positively assimilated to their peers. So which means that if their peers defaulted, they started defaulting as well. Where for another group of high credit risk borrowers, we saw a negative influence, which meant that if they found that their peers defaulted on their loans, it led them to pay back their loans on time at a higher rate, right? So you see influence, but in two different directions for the high credit risk sample. So again, just by looking at it, you can infer that not only do we see evidence of contagion in default behavior in this particular sample, there is very interesting heterogeneities that you can uncover once you analyze this network in an intelligent way. So a related context, but from a similar for a similar problem, comes from the area of education and student networks. But this is again an ongoing work that ongoing project that I'm working on, which looks at the role of student networks in universities on both academic and economic outcomes. Now, again, there's been a ton of research looking at how student networks inside educational institutions lead to changes in their academic performance and also other related outcomes like, whether they get married, they develop mental health problems, what kind of products or services they subscribe to later on in their lives, etc., and also their eventual successes or failures in the job market. This is a very, very well-studied area. So what we were trying to understand is by looking at a longitudinal data set of thousands of students over a 4-year period, so it's basically an undergraduate educational program, we are trying to understand what are the underlying mechanisms using which students actually form these ties or these collaborative networks inside the university. So are there factors that affect how students make these ties? And once these networks are formed, how do these networks influence their propensity to score higher or lower in their exams? And finally, in turn, does this academic performance impact their job market outcomes in terms of whether they are likely to get a job quickly, are they likely to get higher salaried jobs, etc. And finally, and similar to the previous project, we were also interested to investigate if this element of influence from the network differs based on whether these students are high-performing students, mid-performing students, low-performing students. So this is again a very quick visualization of the network filtered by the different GPA categories. So what you'd notice just by looking at this visualization is as you go through the semesters from semester 1 to semester 8, you see increased clustering of networks. So students form more richer networks, but you'd see a lot more clustering happening with similarly colored nodes. So what this means is you see students forming links, but at higher rates with other students who are similar to them in terms of their academic performance, as reflected by their grades or the GPAs. In fact, if you look at the 7th and 8th semester, which are the final 2 clusters on the screen, you will see there are giant clusters of orange and blue colored nodes, right? So which basically means that students went from a lower GPA to a higher GPA cluster, okay? So this kind of gives you a hint that there is an interplay between how students are connecting with each other in the university and their similarities in academic performance. So we actually fitted the data to a stochastic network model. And I just want to give you a one-slide overview of what we found. So we actually found that for the middle achievers, so this is the middle 50 percentile of academic achievers, they exhibited both homophily and influence, basically meaning that these students formed connections with other students of similar academic performance, but they were also in turn influenced by students with similar academic performance. Now, what was very, very interesting is that we found that for the top achievers in the cohort, these are the top 25 percentile students, they actually exhibited a much stronger homophily and much stronger influence, which meant that they were connecting with other top achievers at much higher probabilities and also getting influenced by them. Conversely, for the bottom achievers, we found a reverse effect. We actually found that bottom achievers were less likely to connect to other bottom achievers. In fact, we actually found evidence of heterophily, which means that they were actively not trying to form links with similar academic performance students. And for influence, we actually found that it's a much weaker influence than both mid-achievers and top achievers. So taken together, this basically shows that there is kind of an evidence that not only is there peer influence in student collaboration networks, but there's also substantial heterogeneity, as is the case with the finance example that I just covered, among this population of students. And so if you're working on a network analytics project, it's mindful to keep in mind that even though you might find evidence of network effects, it's always good to focus on different subgroups within your sample, because you might end up seeing very distinct effects playing out in these different subgroups. All right? So that's actually pretty much what I had for my session. But before I hand it over to Daniel for the walkthrough, let me just quickly introduce the data set that you're going to see for the hands-on session that's coming up next. So this is actually an enhanced version of the Erasmus Mobility Network dataset. So for those of you who are not familiar with the Erasmus program, it's actually a giant academic collaboration program in EU, which facilitates mobility of students and academic professionals among institutions that are affiliated to the Erasmus program. So what this data set does is it merges the mobility of students, staff, and teachers with other kinds of features at a student level, institution level, and at a geographic or location level. So it's kind of, that's why I call it an enhanced data set. So it has the mobility, the basic flow data of students moving between these institutions, but it also has other related information about the students, about the institutions, about places of interest near the institutions and things like that. So it's a very rich data set. And you can obviously think of many different use cases that you can investigate by using this particular data set. So for example, you can just try to plot it on a map and try to see the spatial mobility patterns of students and staff between different institutions in Europe. You can form more complex hypotheses about how network structure might be affecting the rates of mobility between institutions, and many, many potentially other questions pertaining to mobility. Okay, so this is a kind of a summary of the data schema for this particular data set. So as mentioned earlier, this kind of enhances the mobility network for Erasmus students, which has been used in other studies with other databases that provide features relating to institutions or places of interest and other factors. So the merged data set that you see on the slide is what you're going to see in the hands-on session that's coming up next. So again, this is a multi-layer, multi-label spatial network, right? Because you can form different kinds of network based on what you're modeling. And there are many labels for these institutions and cities that you can use for your classification or predictive problem. Okay, so that's pretty much what I have for you from my session. So if there are any questions at this point, I'd be happy to take them. But otherwise, it's over to Daniel.
Hi, okay, so thanks Prasanta for the great introduction to network science and analytics. Definitely helps to put a lot of new perspectives into our daily lives and a lot of new applications that we actually never thought of. So before we move on to the links kite demo, so I think we have a couple of interesting questions and we can take a few minutes to address them. So if you guys have any questions, please feel free to drop them in the session below. So for the first question, so Johan wonders if there are actually any modified measures of centrality when the nodes are qualitatively different. For example, when in a supply chain network, some of the nodes are large corporations and some of these nodes might be smaller firms or startups.
Right. So, I mean, actually, that's a fantastic question, because it helps me talk about something that I did not cover in the interest of time. The fact that network structures tend to be surprisingly universal. So whether you're looking at a large social network from Facebook versus a large network of warehouses in a supply chain, you would be able to see certain common patterns. For example, high clustering, short average path lengths. So a quick answer to your question is you would see certain common metrics that you can definitely use irrespective of what network context you're using, something like degree, average distance, things like that. On the other side, as I mentioned earlier, you'd have to think about what makes sense in that particular context, right? So if it's something like a supply chain network, maybe you're more interested in the idea of connectivity, or how soon you can move goods from one particular warehouse to another. So in that case, maybe a distance-based centrality measure like closeness or average path length or something like that would be a better network measure than something like maybe degree or eigenvector centrality or something like that. So that's a contextual question that you'd have to think about. Yeah.
So for the next question, Rizel asks, what are some of the theoretical fundamentals that one should grasp to go deeper into graph network analytics?
So a couple of things. I mean, of course, having some background in discrete math or graph theory particularly is definitely helpful, especially when you're trying to understand some of these measures and the models. Having said that, it's not very difficult to pick up on, at least on the basics of some of the things that I covered today. For example, what do you mean by the centrality measures? How do you model, say, an evolution of a network over time? What are some of the structural parameters that you can monitor for networks? How do you model a predictive problem on a network? So these are problems that you could pick up and at least get started with relatively few resources. But having said that, I mean, if you're looking into going full-blown into networks, this is actually a semester's worth of content at most universities. So it's always good to start with some graph theory fundamentals, and then going into, say, a network science book, which draws upon those graph theory fundamentals to talk about specific network problems and contexts. If you're actually interested, you can always reach out to me. I can point you to some good resources.
Okay, so we have time for one last question. So based on your experience, what is the effective method to minimize the spillover effect on A/B testing in a social network?
Yeah, so I think that's a good question again. There are many different approaches to doing that. A broad class of problems deal with the idea of what's called cluster randomization. So the idea here is you basically partition the network into clusters so that you minimize links across clusters to sort of minimize the risks of potential spillover. And then you assign entire clusters to either treatment groups or control groups. That comes with its own set of problems. So obviously, if you're trying to estimate or come up with a more unbiased estimator, you'd have to make a few more statistical corrections to that. But generally, the idea of graph cluster randomization is a popular approach that you could use when you're trying to do some kind of a randomized assignment on graphs. That's just one solution.
Okay, great. So that's all the questions we have for now. So
sure.
I think we'll hand over the time to Daniel for the Link Skype demo. So yeah, Daniel, please.
Thank you very much for this great introduction to network science. I hope everybody is very inspired to start doing network science immediately. And I want to make sure that you can get started with network science as fast as possible. Oh, there's another question. Will this session be recorded? Yes, I think it will be recorded, right? I think so. Yeah, okay, right here on this stream. You can watch it later as well. Okay, thanks. So then, like this is a branch of data science. So what does a data scientist do when they want to do something with actual data? You get out a Python notebook and just have at it pandas. And well, for network science, there are some very good Python libraries. And like NetworkX is super popular, but it's pure Python. So if you have a sizable graph, it will be a bit slow. But there are NetworkKit, I like very much, is a high-performance C++ library with a Python interface. You can also get started with that. And there, you can combine it with TensorFlow and PyTorch. But all of this, just, well, the learning curve is a bit steep. And we have just open sourced Linkskyte like a few weeks ago, maybe a month, that you can see on which side? There it is, Linkskyte. I will show you how much easier it is, because so it allows you to get started without writing any code, but it also allows you to, as you grow more experienced, you can combine it with Python coding very easily. That's a big focus of the tool. So it's called Linkskyte if you want to look it up, and let's see how it works. So this is an empty workspace right here, and I'm going to drop some file in here. I have a CSV file just extracted from this beautiful data set that Santa has introduced. Now it's getting uploaded. Depending on my bandwidth, we will see a result. So there's some error. I think there are some malformed records inside it, but I can just open it and tell it to just ignore the malformed. Wrong button. Okay, so here importing a CSV has a million options, but one of them is what to do with malformed lines. So we will just drop those lines, and let's see. So I should have it's semicolon separated, so that's why everything is malformed. Sorry, good thing I'm doing this live. So the delimiter is a semicolon. Well, already, if you were doing the same thing in Python, you hit all of these, but each time you have to look up the documentation. What is the parameter to tell this library to import, to use semicolon as a delimiter? You have to look everything up on Stack Overflow if you're like me. With Linkskyte, it's a bit smoother, hopefully. So now we have this beautiful data here. What do we see? There are lots of columns, and they tell us about which year this was. So each record here is one student going from one university to another. And this is the from identifier, and this is the to identifier. So when you start out with network analytics, that's what you are looking for, the source and destination of each edge. So each record here is an edge in a graph. But now we look at that as a table, but you can build a graph from it with, let's say, use table as graph, and just connect these. And now we have a graph, except we have to tell it like which columns are the source and destination. So the source is the from, and the destination is the to. Immediately, it starts churning the CSV file, and we will see it's finding the edge attributes, and it found 3,000 something, 2,800 universities and 59,000 edges. We can, like, what do we want to do with this graph? We can take a look at it, always a good first step. Now we will just see a small sample of this. So I don't want to put 59,000 edges into my browser. Okay, so that's what it looks like. We can put this identifier on the vertices as a label. So we see, okay, from Riga to Brno, and we can increase the sample radius, so we see some more of the graph. But what I want to show. It's a bit random. Yeah, depends on which sample we are looking at. But very quickly, if you look at a sizable sample, like this is just 120 edges, but already the data looks like completely meaningless, right? So there's nothing that a human could spot in this data set just by looking at it. But luckily, this beautiful data set has also some CSV files that tell us a bit more about the universities, such as their physical location, the GPS coordinates. Oh, is this data set also semicolon separated? Let's hope. By the way, let me know if you can't see my screen. Okay. Oops, what have I done? Malformed record. Excellent. All right, I remember this. There were some comments. So it's exported from an Excel file actually, and that had some extra stuff in it. But now, where is it? Yeah, it is actually comma separated. Very good. So I know that I'm making a lot of mistakes here, but worry not. I actually have a very complex prepared workspace, and soon I will switch to it. I just want to give a high risk demonstration of like how it works in reality without any sugar coating. So here we have for each educational institution, we have the latitude, longitude coordinates. I think this is the position of the city, and this is probably the position of the university within the city, right? So I think we will use these for visualization. And how do I do that? So now I have a graph already, but I want to join this table to it. So for that, So in this table, each record is one university. So these will be attributes of the vertices. So I say use table as vertex attributes, and I just connect it like this. And the graph is this graph. So we join them, but we have to say what do we want to join by. The vertices only have this one ID attribute, but here, this is the Erasmus ID column. And just like that, suddenly, now all of the vertices have really a ton of attributes. This is a beautiful data set. So city, country, name, number of students, and so on, teachers. Yeah, let's put it on a map. So I want to visualize it as a geographic location. And for that, we have to put those separate numbers, bundle them into a single attribute. So these two I will call position. And this creates a vector attribute out of those two numbers, which can be used for visualization, but also when you do machine learning and you want to build a feature vector, that's how it is. So now, yeah, this is a visualization, and the visualization has a million parameters. Do not be scared. But this is how we can choose, like, we can put the country as a label or something. But more importantly, now we have this position attribute, and we want to use it as actual geographic positions. And then immediately we get something that's on the map. And that is the human mind can immediately comprehend it much better. Now we see that there's a university in Poland. Sorry. Yeah, this university in Poland is sending a lot of students to Spain. The weather is certainly better there. Although, not right now, right? Or the people having a heat stroke in Spain would argue otherwise. So I think with that, I will switch to the prepared workspace, where I don't have to risk any misclicks or anything. And Linscat has this little file browser where you can pick up your workspace. So this is a huge workspace, but you can zoom the other way. Yeah, this is probably too far to zoom out. But what we have here is importing the same CSV files and then combining them with these university attributes, use table as graph. What happens before it is there's a separate table that decodes the numerical subject IDs, because in this table, the CSV that we imported before, there's a subject, but it just has 310. So I just write Linkscat's one of the best features, I think, is that it seamlessly allows you to combine SQL and graph theory. So in SQL, you can easily join two tables together, and that's what happens here. I have two tables. One of them has this decoding, and the other, so one is the table of the students with the numerical code, and table 2 is has the resolution for that. So we get the description from there as subject name. So now the graph will have a subject name attribute. And oh, where is it? Oh, the edges have the subject name attribute, of course. So one thing we were talking about is how the degree of vertices in a natural graph is usually its that distribution has a long tail. So with these boxes, I'm just computing the degree. I'm computing the 3 different degree metrics in degree, so like the number of students coming to visit this university, out degree, the number of students going away from here, and the total degree, just the sum of those two. And we can see that if you look at the histogram, there's a sharp drop-off. So many universities have a low degree. Even if we look at, it's better to look at it logarithmically. Then it's somewhat uniform up to a point, and then there's a sharp drop-off. So there's a very long tail. Even on the logarithmic side, we can see this. And these are super popular universities, like the biggest universities in Europe. They have thousands of students participating in the Erasmus program. While we also have many universities that are of different sizes, small and medium-sized. Okay, and like if I compute with this box, I can show how to do some simple computation. This is great in Linkscat as well. You can just you say I have a formula in mind. In this case, it's very simple, just subtracting the input degree and output degree, and just I want to compute degree difference and using this formula. And if this is actually Scala code, so you could type whatever, but I don't want to mess up this beautiful prepared workspace with anything crazy. But so now I can now make a small visualization where I visualize all the universities and color them based on whether more people are coming in or more people are going away from here. Will it load, or will my browser crash? Okay, maybe I shouldn't. It's too late to think about this, but I could merge the universities by country, I guess, or something, so that I don't try to show thousands of points. With great difficulty, we have loaded this visualization. Zoom, zoom, zoom. Everything worked better when I wasn't streaming. And so if we zoom in now, we can see that this is too much to visually comprehend, but there are places with, so purple is more people going out, and green is more people coming in. So there are some popular tourist destinations, universities, and other universities that are more contributing visitor students. I think this all looks much better if we, if I do this merge vertices by country. So yeah, I guess you've noticed that Links Guide has this interface with boxes where each box does something, and you can just connect them together as you like. And this is great for experimentation. Like in a Python notebook, you would have to, if you want to change something in an earlier step, like adding these merging operations before all the degree computation and whatnot, then you would have to, okay, you add the code and then you rerun all the cells. And well, that's fine. And I'm used to that workflow as well, but Linkscat is even better. Like I just change the connection and it automatically refreshes the visualization. And now it's easier to see, definitely easier to see when aggregated over countries. Like Germany is a big contributor of visitors, and the UK is a huge sink. Like a lot of people go there, and not a lot of people visit from the UK other parts. Interesting to know. And maybe, yeah, we can think about. Okay. Sorry, I'm looking at my notes. I don't want to waste time going on a rampage here. So let's focus on what I wanted to say. So what I will focus on is just to, so we can see that universities have different popularities, right? And we want to see what causes that popularity. Like why are some universities so much popular than others? And quick ideas, like first hypothesis, maybe it's just the country. Like everybody just loves visiting the UK, so maybe that's it. And for this, I can look at it like this, or no, yeah, before aggregating them by country. So abandoning this pass, we are unaggregated again. Each point is a single university. Yeah, and this visualization, it breaks down. So on the x-axis we have the degree, while on the y-axis we have countries. Of course, not all the countries fit on this chart, but it picks the most popular ones to put here. So France is most popular, and we can see that we can see the degree distribution for France. And it's, yeah, there's definitely some interesting effects here. Like in Spain, there are lots of low degree universities. And when we highlight a node, we can also see a bucket. These are buckets, right? So there are 95, okay, just to explain what we are looking at here. Sorry, I'm just too used to this chart. So this bucket it has degree between 1 and 3, and it's in Spain. So there are 95 universities in Spain that have degree between 1 and 3. Small universities, or maybe the university is big, but they don't participate with a lot of students in this program. And the other buckets highlighted are universities that are connected to this one. So as we move the mouse cursor, we can see some of the connections highlighted. And well, for these very popular things, even the edges are more visible. Okay, but anyway, yeah, interesting stuff. I don't want to go into too much detail about what we actually see. You can read it for yourself. But it's just want to show a lot of methods, right? What stuff we can do with graphs. So another idea is that maybe the popularity depends hugely on the subject. Like, so to test this, the subject is a property of the edges. So it's not so easy to just immediately look at the distribution. Like, so correlating degrees and subjects, because when we look at our graph, it has the degree for each node, but it has the subject for each edge. but there can still be, of course, correlations. So what we can do is we use this aggregation box and just aggregate some attribute to the, we aggregate along the incoming edges, and we aggregate the subject name, and we pick the most common subject name. So now each vertex gets a new attribute, this one, edge, subject name, most common. So it's the most common subject name on the incoming edges. And now we can visualize this against the gray. What will we see? Seems somewhat boring, but we can see for engineering the distribution's peak is actually at a medium-sized universities. For social sciences, I guess it's even bigger universities. For humanities, it's roughly evenly distributed between small and big universities. So that there are some differences according to the subject, and we could dig deeper in that or think of that as a result. But other options for doing the same check, so we can also, where did I put that? Yeah. So we can, yeah. So maybe we want to look at the degree distribution when we, so we can use SQL to just throw away all the data that is related to some other subject. So it's just the social sciences students in this table after the filtering. And we start our whole analytics from there and look at visualizations that way, make comparisons like that. Okay, another option is to do this computation in Python. You can drop down a box, a Python box, and just use pandas here. So ES is a pandas data frame that has DST and SRC columns for the vertex IDs. And then we just compute these restricted degree metrics. So just the degree of a university when we only consider the social sciences students, the degree of a university when we also only consider humanities students. It's a small piece of code I wrote, and it actually works because I didn't write it live, right? And we can now create a histogram from this and see the degree distribution depending on the subject on a single plot. Again, someone who is actually looking to understand something and not just demonstrate how to use this thing, they could derive some insights from it. But what is only obvious is that science students are underrepresented in this data set, or there are fewer of them in the program than engineering or humanities. Good. Oh, another idea. So another possible explanation that we can think of, like why is a university popular, is because of the pubs. Maybe it has good pubs. So thankfully, this data set includes data about pubs. It includes data about everything. Beautiful data set. So here we have the different pubs, I guess, but also shops and even parks and traffics. I don't know. So anyway, it's nicely categorized. So we will just look at the categories, but you also get super fine-grained data like the actual geographic location of that shop and how far it is from the university. So you could do much more sophisticated analysis. But I will just use a simple SQL, like create these aggregate variables. Just so each record here is a pub or park or something, and I just want to count the number of bars for each institution. Erasmus ID is the institution ID. So I group by institution, and I sum the bar score. The bar score is 1 if this if this point of interest is a bar, then it's 1, otherwise 0. So bar is now just the number of bars around that university. I again use table as vertex attribute. Oh, I should have zoomed in more, right? Sorry for thinking of this too late. But now I join this to the graph. So now our graph has a bunch of new vertex attributes for number of bars, number of parks, number of restaurants. And we can easily look at the distribution of that as well. It looks like even the number of restaurants also follows a similar distribution as the degree. So there's a long tail. Like some places have insane number of restaurants. Well, insane. I guess it goes to 58. Even this histogram tool is nice. Like you can just click on something and it zooms to that, so that the one I clicked is now normalized to 50%. Some of them are clipped now, but the rest we can see more clearly. Or we can just say, like, I want filter to those that have greater than 20, greater than 30. You just see a part of the distribution like this. Okay, but then discard the filters. Back to this. So our hypothesis is that somehow this has something to do with the popularity of the place. So we can look at a scatter plot and just eyeball it like the professional data scientists that we are. Yeah, okay, so it's again a lot of points, and it's colored by country, but like it's absolutely impossible to derive any insight from this. Looks like they are not extremely correlated, right? So this is these places, these universities have more food places. Apparently, yeah, we can see that there's a cap on the number of food places included in the data set. So maybe these have hundreds or millions of restaurants. We will never know because the data set only lists, I guess it only lists the first 58 restaurants. Strange point to cut off, but here we are. But it's not like there's no diagonal shape or anything that would suggest that these are correlated with the degree. But maybe they are, and it's just like old human eyes that are too weak to see the correlation. So I just dropped down some regression model to, yeah, now I will just show some machine learning features. Like maybe the machine learning model is able to spot some correlation here. And yeah, this box, it splits the data into train and test set. You just drop that down, and then you select which attribute to train on, and you train on the training labels. So those labels are now undefined for some part of the universities, so that we can do the verification. And yeah, we got a model out of it. We can see which correlations it has discovered, and it says that food is like absolutely not a good indicator. Culture is, and parks are the best indicators. But even having identified these and giving them a bigger weight, it still ends up with a very weak correlation. So the whole model is like it's not a random guess, but it's very close to guessing the mean value for the degree. So we are a bit sad about that, but we can try some other models and see if anything is better. Like a decision tree, it has more degrees of freedom, right? Or we can do a deep learning model, graph convolutional neural network, a GCN. And all of these are just pop down and use basically the default settings. Just for the GCN model, I just bundled everything into those vectors because that's the format it likes. this is actually PyTorch based. It's PyTorch geometric based. Yeah, if you're familiar with that. And then what I did, I use all of these models to make a prediction and then compute the error. Just, again, it's a simple formula. I compute the squared error. I just subtract the prediction from the test labels and just multiply by itself to get the squared thing. And then this is another aggregation box. So Linksgeist has all sorts of aggregations. Because all the time when you do network analytics, you want to do things like this. I want to compute the average of the network, average of the neighbors, of the average value of some parameter on the neighbors, or but just only on the incoming edges or only the outgoing edges. Or I have found some communities in the graph and I want to compute the median across each community. Yeah, we do this all the time, and there's a great variety here. Maybe you want some weighted aggregation, anything here, we have the box for you. And yeah, so what I do here is use these aggregations to compute the same error metric. And here it's almost 1 million with the decision tree. It's somewhat smaller, 700,000. And with the graph convolutional neural network, I guess it's even lower. The graph convolutional neural network is super nice because it doesn't just look at these labels. Like the first two models, they were trained just on these 4 numbers, right? The number of bars, number of parts, and whatnot. But the GCN, it also sees the network itself, so it can use that for training, which is maybe an advantage. And yeah, it gets the lowest error. Okay, and I've mentioned the communities. Actually, I have no idea how much time I have left. Sorry, let me quickly check. Maybe very quickly, because it gives us another nice chart. So very often you are wondering, like, does this graph does it have any communities? And here it is. We have some boxes related to that. Fine modular clustering is a safe default. Like it just modularity is a nice network clustering metric when you have. So you can just cluster nodes in a network sort of randomly. You say, this is a group, this is another group, okay. And there's another clustering which was created by some other algorithm. And okay, which one is better? And modularity is a metric for a clustering that can tell you exactly this, which is better. Because yeah, it tells you how many, like you can say that if I just randomly do some clustering, what would I expect? How many edges would I expect to go within the cluster? And how many would I expect to go between 2 clusters? Just based on the sizes of the clusters. And then there is the actual number of edges going within and going between clusters. And of course, what we want to see is that there are many edges going within the clusters and there are few edges going between the clusters. So this means that these are real communities. They are densely connected inside and sparsely connected outside. And this box, it's just an optimization algorithm that tries to find an optimized clustering group, optimized for this modularity metric. And then we can look at it. Yeah. What we find is that, okay, so these are the clusters it has found, and the number is the number of universities in that cluster. So I'm highlighting on this side the universities that are actually in this cluster because the stream is overwhelming my machine. I will just look at some of the smaller clusters. Yeah, so this cluster just contains these 2 universities, but we have also identified some fairly large clusters with hundreds of universities that are connected according to this. And we can see, okay, so is this a geographic connection? Based on the few samples we've seen, it's not, but who knows? So we can look at the visualization where I'm coloring based on the segment ID, based on the cluster ID. So if it's a geographic thing, we would expect to see lots of color, like maybe Eastern Europe is green and Northern Europe is yellow. I can tell you what we will see. It won't be like that. It looks like it's completely randomly colored. Again, I'm loading all the universities in one visualization. Sorry. Yeah, so it will appear beautiful but randomly colored. Sorry. Yeah, once the animation stops, you can know that, and this has already stopped a long time ago, you can know that it's no longer Linkscat that is slow, it's my laptop. In the meanwhile, let me check if there are any questions I could answer, because we are very close to the end. Like this was the last thing I wanted to show. Yeah, there's one question. Okay, so it has loaded, but in the meanwhile, Rizal on YouTube has posted another interesting question about training machine learning models and whether you can do it in Python. And yes, I'm preparing a blog post about using scripting in Linkscat, because there are so many different ways to do it now. So one option is you can use a Python box that I have already shown, where you can write your Python code and maybe do some machine learning in Python, and it's integrated into Linkscat's whole thing, right? So you do the machine learning in Python, but for visualization, for SQL manipulation, for importing files, you still use Linkscat, and for experimentation, it's a great environment. But for, if you want to experiment with cutting edge new machine learning models that haven't been integrated into Linkscat yet, then you can do it in Python. Another way is to do it the other way. Like maybe you want to use a machine learning model that is already in Linkscat, but you want to do it from Python for some reason. Well, that reason can be that you're working on automation. Like a very typical use case for us is that you've prepared, you're a data scientist, you've done the work in Linkscat, and you've got some result. And the result is maybe some actionable thing, like a scoring that we want to use for advertising on these university campuses, right? We want to advertise this Erasmus program on universities that we think would welcome participation. Maybe we predict that this university in Ukraine would very much like to send students to this university in Norway, because the machine learning algorithm has identified similar patterns, but it shows that this particular connection, it gets a high prediction, but in practice, it gets a low participation. So maybe it's just a matter of awareness. And for that reason, okay, so yeah, every day we want to update this prediction with the new data as it comes in. So you probably want to do that in Python. In the meanwhile, I've opened something completely different, but first I will finish that train of thought. So we want to do that in Python. And then, okay, I will just close it. So you can choose some part of the workspace, and you say, I want to run this in Python. You just click on this Python button. Okay, I didn't choose the best examples of this because the visualization box is super complicated in Python. And maybe you want to do the modular clustering and then the aggregation and then discard the edges. Okay, and you want to do this in Python, click this button, and you just get this little bit of Python code. And it's actual Python code. You can copy paste it into Python, and with a few, like you have to provide the input as a Python variable somehow, right? And we just assume that this will be the name. But if you start from a CSV, then you don't have this problem. But okay, so you copy paste this thing and put it into your Python script. And if everything is set up correctly, then this will just work. And there are a few other ways of doing Python automation in Linkscat, and not just Python, we have Scala and SQL integration as well. So I hope that's, I guess that must be an exhaustive answer to the question. And just the last thing I wanted to show is this. So now each column is one of the clusters. We have identified, I think, 9 clusters. The cluster IDs are super long numerical strings, so don't worry about that, but each column is one cluster. And we can see that now this is actually a highly correlated data, so this clustering is actually something meaningful. We can see that like this cluster, it's only about engineering, right? The other sciences are barely represented in this cluster. While, I don't know, this other cluster, it's all about humanities and arts. There are 3 separate clusters identified in social sciences. And there's some overlap with humanities, I guess. And so, yeah, we got something meaningful out of this data set in the end. And that's it for me. I'm very happy to get some more questions. Ivan, you're muted.
Myself. Thanks, Dan. Thank you so much, Daniel, for the walkthrough of the Links Kite application. I can definitely see that it's a very powerful platform. I like how I really like the flexibility of being able to integrate with Scala, Python code, and even the ability to superimpose on maps. So I'm going to, we will spend the last few minutes to answer any questions. If anyone has any last questions, this is now the time, because we are actually towards the end of the event. So yeah.
I just remembered I have some slides. But yeah, it's just, I guess it's about another use case. I don't think it's, I will just put it up, but I don't want to talk about it too much. Better if we have some questions. And you can download Linkscat to try it. It's on Docker Hub, so I think that's the easiest way to get started. Just Docker run Linkscat/Linkscat. But also we have small free demo instances online. If you go to demo.linkscat.com, it takes a minute to boot up, but you get your own test instance. Or go to linkscat.com and see there are some other ways you can get started with it.
Yeah.
It's these algorithms we have, and then there's this demographic prediction use case. It's an actual industry use case. If you're interested, I'm happy to field ask questions about that as well, or pass them on to Phi, who can better answer.
Okay, very interesting. More use cases. I think we have no further questions. I would like to once again, I want to thank Prasanta and Daniel for taking the time out to share with the community this evening. I think this has been a very great session. So and last but not least, I also want to thank Jiaxing from Google Developer Space Singapore for helping for hosting and sponsoring the event. So we hope you enjoyed today's session. Stay tuned for upcoming events that we still have a lot of events lined up all the way until the end of the year. And yeah, we hope you enjoy your long weekend. See you guys.
Thank you for organizing it.